All right, welcome back to another exploration with exponents. At this point in our practice, we should be able to identify when to add exponents, when to subtract them, when to multiply them. Also recognize exponents of zero, exponents that are negative, exponents that are fractions. Those are some of the basics that most students can identify pretty easily. However, one that is very easy but very rarely used is something like this. We always look to recognize for same base, and then we can do something with the exponents. But look at these two examples where the base is not the same. This seems to throw off students sometimes. Let's just explore it and see how easy this can be for us in the future, all right? And I'm going to do that by, let's use expanded form. Unless you already recognize, just bear with me and we'll check the answer soon. All right, so what I see is 4 to the 5th. 4 to the 5th. How many times is 4 being multiplied by itself? It is 5 times. So 4 times 4 times 4 times 4 times 4. Then what's going on with that? We're multiplying this 3 by itself 5 times. Or we can continue this product. I'm going to write it in parentheses. 3 times 3 times 3 times 3 times 3. That's what's going on, right? That's the expanded form. And then the nice thing about this is that we're multiplying these two expressions in whatever order we want, because order doesn't matter. So one thing that we can say is, all right, let's suppose that we say we'll multiply this one by this one first, and that's 12, right? So it's 12, and what's this one times this one? Times 12. Whoops. And you can see what's going on. Times how many more of those? Times 3 more 12s. I don't know if that was a very good visual for me, but that's what's going on. See, there's 4 12s. If we rearrange them in that order, which means that this is 12 to the 5th power. So the question is, what stayed the same and what changed? Look, the exponents stayed the same. There's still an exponent of 5. And what changes the base? And how did that 12 occur? It's because we have 4 times 3. That's what's going on. And just to rearrange it in a different order, we could have said, instead of multiplying it, we could have left it in represented form. So we could have said 4 times 3. That's how we got this 12 here. How did we get this 12? By doing 4 times 3 again. And how do we obtain this 12 in the middle? By doing 4 times 3. And so on. 4 times 3 2 more times. And what I'm trying to show is that we could also represent it as 4 times 3 to the 5th power. And there it is, 2 equivalent forms. So this is the most compact, and this is like it's still compact, but it's more, you can see where that 12 is coming from, all right? Because that is the form that the next one is represented in. So again, let's represent this in expanded form is, because this is in parentheses, now I'm going to think of it as something to the 4th power. Something to the 4th power will look like something times something times something times something. What's the something inside? It is 6 times 9. 6 times 9, 6 times 9. And you can know what 6 times 9 is, right? It's 54. So 2 ways of rewriting this one. Again, this is the expanded form, or we can say this is the same as 54, 54, correct? Yep, 54. I won't use the parentheses anymore. 54 to the 4th power. Where did that 54 come from? The product of 6 times 9, but only because the base is the same. That's the key idea to identify. Here's a 54, here's a 54, here's a 54, here's a 54, because it is each one of those 4 times. Cool. So seems to be another thing that we should be able to recognize with the exponents. And the key idea is the exponent's the same. The base can be different as long as the exponent is the same. Look at that. These 2 bases are different, but they share the same exponent. These 2 bases are different, so they share the same exponent. Therefore, we can do that. So that can be helpful because at some point, especially if the exponent is x, then I won't be using expanded form anymore. But what we recognize here, the thing to recognize is same exponent. Therefore, what can we do with these bases? It is multiply them. So we can say in 2 ways, I'm going to write it. We can say 7 times 4 to the x power, which is the same as 28 to the x. This is going to be a powerful idea for us in the future when solving equations. And let's move on. So the key idea is to identify what? Same exponent. Different base, the base can be different, but as long as the exponent is the same. So what's going on right here? Do we have the same exponent? And the answer is no, we don't have the same exponent, but therefore we need to do some simplification first. And what we notice is we have multiplication of exponents, something I talked about very early in the video. For what operation or what case do we scenario do we multiply the exponents? And that's when we have a exponent raised to another exponent. So therefore we can rewrite this as 2 to the third to the x, like this, 2 to the third to the x, or we can rewrite it as 2 to the x to the third. But which one's more convenient for what we're doing? It's going to be, can we simplify this further? And the answer is no. Can we simplify this one further? And the answer is yes. So we're going to continue with the option below. And let's see what happens. This becomes 8 to the x power. 8 to the x times 5 to the x doesn't change. And now we've written them with same exponent, but they have a different base. Therefore, we can take the product of their bases. So we can say 8 times 5 now to the x, which is equal to 40 to the x power. Look at that, a really complex one. We were able to simplify it. It looks like there's no way we could ever simplify or make this look nicer, but we did. Let's use that kind of thinking on the next two. If you would like to try them for yourself ahead of time, go ahead and pause and do so now. And always look again to what's the same or what is not. Always start by looking at the bases. Is the base the same? And the answer is no. So therefore, I now pay attention to the exponents. Are the exponents the same? And the answer is no. So neither the base or the exponent are the same. I'm going to try to get one of those to match. So what I see is, all right, probably not a common base, but we can manipulate the exponent somehow because we have division now, x over 2. Remember that this can be either, write it above first. It can be either a 16, because let's do a little reminder here. I don't know, where am I going to write my reminder? Let's say that x over 2 is the same as 1/2 times x, right? That's a little reminder. So then we can write this as 16 to the 1/2 to the x. Or we can write it as 16 to the x to the 1/2. Which one will be more convenient in this case? I think the one on the left. So let's go ahead and use that one because that can be simplified to 4, right? 16 to the 1/2 to the x times 12 to the x. That one won't change. All right, and we know that 16 to the 1/2 is 4. So that becomes 4 to the x times 12 to the x. That's pretty cool. Now we have different bases, but same exponent, which allows us to multiply their bases. So this can be written as 48 to the x. And there it is. Look at that one. That one, again, looked pretty advanced at first, but it's something that simplifies very nicely. What did you recognize here? We don't have the same base, but look, the exponent is the same. So all we need to do is multiply. Just be careful. You can think of it as 6 over 1 if you're thinking of multiplying fractions. However you do it, it should simplify. The exponent doesn't change. It's still something to the x. But when you have 6 times 4/3, the way I think about it is 2 times 4. I think that's 8. 6 divided by 3 is 2 times 4 is 8. So 8 to the x. That's what happened. That's pretty cool, right? There it is. Same exponent, different base. Same exponent, different base. That's another idea we can incorporate to our practice with exponents. And let's see it in another way. Number 2, rewrite an alternate exponential form, meaning we have, again, same idea of different base, but same exponent. Different base, same exponent. And just to confirm, I will rewrite it in expanded form first. How many 18s do we have multiplied on the numerator? We have 5 of them. So 18 times 18 times 18 times 18. And then we have 6 5s on the denominator. 6 5 6s. My bad. I said that backwards. 5 6s. 3, 4, and 5. All right. And because we do have product and division going on, we can do it in whatever order we want. And let's take this one first. What's this one divided? 18 divided by 6. That's a 3 times. What's this fraction going to simplify? That's a 3. And what does this simplify to? That's another 3. And this one, another 3. And this one, another 3. So we notice that that becomes how many 3s? It is 5 of them, 3 to the 5th power. And do you see a 3 hidden right here? Yep, it is, because it is not very hidden well. It is right here as well. 18 over 6 is 3. Excuse me. Let's do the next one. Just one more expanded form to double check what's going on. Let's expand it. How many 4s are required for the numerator? Is 6. 1, 2, 3, 4, 5, and 6. And what happened in the denominator? There are 6 3s. 1, 4, 5, and 6. And notice that in the previous problem, that was able to simplify nicely. This time it doesn't simplify, but what we can rewrite is the fraction. How many times do we have this fraction? And the fraction is 4 over 3. So I'm going to rewrite 4 over 3. 4 over 3, how many times? It is 6. So there it is. The idea is that this is the same as this expression on the right. We're going to skip the middle part in the future. We're going to go from this, for an expression like this to something like this. I hope you can understand that and not depend on being able to expand it in the future. Because what if it was something like x or 14 instead of 4? You see what I'm saying? So this one's pretty nice. We have two options. We can write, I can think of it as 27 to the 4th. Without expanded form, we can say, oh, you know what? That's just 27 over 3 is 9 to the 4. I don't know if that's the type of example I was going for. All right, well, it worked out. That's the same as that. But look, this one right here has an exponent of x, right? Bases are different, but 8 over 5 can't simplify, so therefore I'm just going to write the alternate form, which is 8 over 5 in parentheses to the x. I think that's what we're going for the alternate form. There we go. That's able to happen because, again, same exponent, even though they have a different base. We can take their quotient now, where before we were taking the product. The next one, do they have the same exponent? So we can use that idea. Nope, not yet at least, but we can rewrite this as 2 to the 4th. I just want to write the two options. I'm going to write the one that makes the most sense. 2 to the 4th to the x over 3 to the x. And what's 2 to the 4th? Why did we choose that? That becomes 16 to the x over 3 to the x. Now we have that idea of same exponent but different base, so we can take the quotient. So therefore this one becomes 16 over 3. Doesn't simplify, so we'll represent it that way. And there it is. This expression right here is the same as this one. See if you can do this one for yourself ahead of my pace. Otherwise, let's check it now. The numerator stays as is, but there's something going on in the denominator that we should change, because k over 2 is not the same as k. Therefore, we are going to rewrite this as 9 to the k. It's the same, or over, I'm sorry, 25 to the 1/2. So again, I'm not writing both of the options, just one of them, to the k, the one that simplifies. 1/2 times k is the same as k over 2. And what does that simplify to? Numerator stays the same. 9 to the k power. I'll write a better k variable. A little better. And 25 to the 1/2, that's the square root, which is 5 to the k. And therefore, we can now simplify this to 9 over 5 to the k. Boom, there it is. That was a pretty cool idea. What's the name of this idea, or how should we remember it? We remember to look for same exponent, different base, allow us to take a quotient, or same exponent, different base, allow us to take a product. So that's the end of this practice. We're going to formalize and put this together in a nice table for you guys pretty soon. All right. So I hope you enjoy the rest of your day, or go listen to some more math videos. But otherwise, that's it for the math practice. Goodbye.